Today we're going to begin a study of the polar coordinate system. Now, up until now, anytime you've been asked to describe the location of a point, you've used the rectangular coordinate system. And the rectangular coordinate system has been very useful to us, and it will continue to be useful because we're going to continue to make use of it. However, we're at the point now in our study of mathematics where we're going to find that oftentimes we are better served by the polar coordinate system. So what I want to do today is introduce you to this polar coordinate system, help you to understand the reasoning behind it, show you how to plot polar coordinates, and show you how to convert back and forth between polar and rectangular coordinates and polar and rectangular equations. Now, let's begin by just trying to get an intuitive idea about what's going on with these polar coordinates. Let's suppose we have a point, and we want to describe the location of that point. Well, we know how to do that. With rectangular coordinates, we find the x, we find the y, and we have an ordered pair. There we have it, x and a y. But now, let's look at things a little bit differently. Let's suppose that from the origin, I just draw a line segment up to that point. Now, when I do that, an angle is formed here with the x-axis. Now, if I know the value of that angle, I'm on my way to knowing the location of this point. Because if I know the angle here, how much of a rotation there is here, all I have left to know is the distance from this origin up to that point. Now, if I know that distance, I've described the location of that point. I know where that point is. Well, this is the idea with polar coordinates. Just like with the rectangular coordinates, we have the x and the y. With the polar coordinates, we have the r, this distance here, and the theta, this angle. And that describes where that point is. It's just a little bit different way of identifying the location of the point. Now, let me just talk about a few terms that we're going to, that you'll be hearing from time to time. When you want to construct a polar coordinate system, you start off with a fixed point, a pole, or the origin. And from that origin, you draw a ray, and that ray is called the polar axis. Now, we use this to identify points, or the location of points. For example, this point we're calling P. And what we want to look at is the angle that's formed here. We're going to call that the directed angle. And notice I refer to it as the directed angle. It can be negative. In other words, whether or not the angle is positive or negative matters here. And we've been looking at angles that are generated from counterclockwise rotation. So we've had positive angles. And then you have this directed distance, r. Notice it's a directed distance. It can be negative. R can be negative. So here we have the pole, the polar axis, the directed angle, and the directed distance. And these things compose this polar coordinate system. So we'll make reference to these terms throughout. Now let's look and get right into plotting polar coordinates. Let's consider this point, these polar coordinates, the r is 3, and the theta is 210. Now what I want to use is a polar grid. It's a little bit different from the rectangular grid that you're accustomed to. The rectangular grid, remember, has the x and the y-axis, and then intersecting horizontal and vertical lines forming little rectangles. Here, instead of little rectangles, we have concentric circles. And these little lines here you can think of as terminal sides to angles. and the longer ones represent terminal sides of angles that we associate with the unit circle. In particular, here we have the 30 degrees, 45, 60, 90, and so forth. And the shorter ones are not associated with angles, any angle that we identify as being part of the unit circle, any of the special angles that we use from the unit circle. So let's suppose that I want to plot these coordinates. Well, I start off recognizing the 3, the r, that's the directed distance from the pole. And then I simply plot this 210 degrees. Well, here's 180, 30 more would be 210. So our angle is here, and we're finished. We've just plotted those polar coordinates. Now let's look and see how we would handle the situation where we have a negative angle, a negative 210 degrees. Well, we approach it the same way. Notice you have the directed distance has not changed, but now instead of plotting counterclockwise, instead of going counterclockwise with the 210, we rotate clockwise and we end up over here in quadrant 2. So that's how we deal with the negative angles. We're just going back to when we learned how to graph angles. It's no difference, but now we're given a directed distance. Now, here's what we want to look at next. What happens if the r is negative? For example, what about negative 330? The way I approach this problem is I ignore the negative altogether at first. I just plot 330. And then I recognize this, that negative just means you're going in the opposite direction. In other words, you're reflecting across the origin here. So this point here, that's not the point, that this is not that location. The real location is over here across the origin. So if you were to connect the correct point here with this starting point, this line here, of course, it's just a straight segment. There's 180 degrees. So if I add 180 degrees to that 30, I would get this 210, and that's the correct point. So I just start off plotting without regard to not regarding this negative at all, and then I just know that I need to reflect it across the origin. That's how you can get a real quick sketch of that. Now, this brings up a couple of things here. If you have negative r theta, that's the same point. This describes the same location as this. Drop the negative from the r and just add plus or minus 180. That's like what we did with the previous problem. Negative 330 is the same as 270. And here I have the same thing, the same statement, only using radians. Instead of 180 degrees, I'm using pi. Now, this brings me to this point. Remember that when you have a point and you're wanting to describe the location of the point using rectangular coordinates, there is a unique ordered pair that describes that point. Well, that's not the case with polar coordinates, because these thetas all have coterminal angles. So, for example, if I have r theta, those coordinates, that describes the location of a point. Well, if I add 360 to theta, that's a coterminal angle to theta. So that also describes the location of the point. If I add 360 times 2, that also describes the location of that point. In other words, as long as k is an integer, this r theta is the same as r theta plus 360k, where k is an integer. And looking at it in radian, describing it with radians, r theta is the same as r theta plus 2k pi, where k is an integer. So that's something to keep in mind. It's because since we're using theta, theta has coterminal angles, in fact an infinite number of coterminal angles. It differs from rectangular coordinate system in that way. Now let's look at the relationship between the coordinate systems, polar and rectangular. Let's just suppose that we have a point and we have a directed distance here of 1 and the angle of 30, so that the polar coordinates are 1 and 30. Now, from that, let's see if we can find the rectangular coordinates. And I want to proceed this way. I want to just drop a segment down here such that it's perpendicular to this axis. And what has happened now is we have a 30, 60, 90 triangle formed. And that's good because that triangle has some interesting properties. One is we know that the side opposite the 30-degree angle is 1/2 the hypotenuse, and the side opposite the 60-degree angle is 1/2 the hypotenuse times the square root of 3. So look, we have the x and the y, the rectangular coordinates for this point. The x is here, square root of 3 over 2, and the y is here. So what we have done is we've started off with the polar coordinates, and we found the rectangular coordinates. Now that's what we want to do with this segment here. We want to be able to convert back and forth. So we're going to see if was there a general relationship here. Now let's look at what would happen, just for emphasis. I've got the same situation, only now instead of a 1 unit here, I've got 2. And now notice 1/2 of the hypotenuse is 1. 1/2 the hypotenuse times the square root of 3. And once again, we've got the rectangular coordinates. Now, let's look at just a general way to convert from polar coordinates to rectangular coordinates. Okay? Now, instead of the 30 degrees and the definite value for the distance here, I've just got r and theta, and here's a point. Now, of course, here we have our y coordinate, and here we have our x. This distance here is x. This distance is y. Now, look at this. We've got these coordinates. We know the rectangular coordinates are x and y. But we want to see, okay, is there some kind of relationship between x and y and r and theta? Well, notice, sine of theta is opposite over hypotenuse. Y over r. So what we've got here is we've got theta, y, and r all together in an equation. If I solve for y, look at this. I get y is equal to r sine theta. We have a relationship. If we know r and theta, we can find y. Likewise, the cosine of theta is adjacent over hypotenuse. Solving for x, you get x is equal to r cosine theta. Now we have a relationship. If we know r and theta, we can find x and y. If we know the polar coordinates, we can find the rectangular. So in fact, the rectangular coordinates are r cosine theta, r sine theta. Let's look at an example. Let's suppose we have 360. We have these polar coordinates and we want to convert to rectangular. Well, we remember that x equals r cosine theta. Now in place of r, I'm going to put the r. In place of theta, I'll put the 60. And we remember that the cosine of 60 is 1/2. So here we have 3 times 1/2 equals 3/2. Now, let's do the same thing for the y. Y is r sine theta. Put in the 3 and the 60. And we have 3 times, now remember the square root of 3 over 2, that is the sine of 60. And this is just equal to 3 square roots of 3 over 2. So the rectangular coordinates are shown here. 3/2, comma, 3 square roots of 3 over 2. Now let's look at going from rectangular coordinates to polar. Okay, so we've got our rectangular coordinates. And what we want to do is figure out what the r and theta are. Now, first of all, we recognize this, that the Pythagorean theorem tells us that x squared plus y squared equals r squared, because this is a right triangle. So notice right away we have a relationship with the x, y, and the r. We take the square root and we get r is equal to the square root of x squared plus y squared. So that tells us that if we know the x and the y coordinates, we can find the r coordinate. Now, we just need to figure out what theta is. So we need a relationship that involves theta, the y, and the x. Well, tangent does that. Tangent theta is equal to the opposite over adjacent. That tells us that theta equals inverse tangent of y over x. Now we're going to find we have to be a little bit careful with using the second one. Theta equals inverse tangent of y over x. But nevertheless, these are the formulas that we're going to use to go from rectangular coordinates to polar. So let's look at an example. Convert the rectangular coordinates to polar coordinates. So there are the rectangular coordinates. So we start off by looking at the graph. Now I always do this. When I'm given rectangular coordinates and I'm going to convert to polar, I want to look at the graph first because, well, that's going to become apparent here in just a second. But I want to see if I can figure out which quadrant that point is in. So I do a quick sketch. It's easy to sketch that point because we're accustomed to sketching rectangular coordinates. So here's what we have now. What I want to do next is find the r. And r is easy. We take the x squared plus the y squared, the square root of that. And of course, this one works out just to be 1. So we have our r. Now we just need to find the theta. Okay, theta is going to be the inverse tangent of the y over the x, which is going to be 1 over the square root of 3. And that will give us 30 degrees. So we have our rectangular coordinates. Our polar coordinates, 1, 30. Okay, let's look at another one. Now, notice we have negative square root of 3 over 2. Now this is important because we can't just plow in here and not be aware of what's going on. We need to know where this point is. Now notice this negative x value puts us in quadrant 2. The negative x and the positive y puts us in quadrant 2. Now let's proceed on. Let's find their r. Just being aware of what quadrant we're in. And once again, it looks like our r is 1. Now let's find the inverse tangent of y over x. And now we get the inverse tangent of 1 over negative square root of 3, which gives us a negative 30. Now that is in quadrant 4. That's not what we're looking for. We don't want quadrant 4. We need an angle that will put us in quadrant 2. But the problem is whenever you put in inverse tangent will only give you output that's in quadrant 1 or 4. Inverse tangent will not give you output that's in quadrants 2 or 3. So here's what happens. We can see that, yeah, this is not the angle that we want. Negative 30 is down here. So what we have to do is we have to make an adjustment. Okay, that's quadrant 2. This is quadrant 4. That's a problem. But it's an easy problem to solve because the true angle can be found this way. We recognize this is negative 30. This is the angle we want right here. Well, all we have to do is add 180 onto that angle that inverse tangent gave us. If we add 180, we get 150, and that's the angle that is our focus. So that's the way we handle that situation. When we get an angle that's not the correct angle, just add 180 to it because that will fix the problem. Now, let's look at the summary of the coordinate conversion. If you're talking about going from polar to rectangular, you just remember you're given polar. To find the rectangular, just take r cosine theta for the x, r sine theta for the y. Very simple. Now, if you're going from rectangular to polar, remember the r is the square root of x squared plus y squared. The theta is equal to inverse tangent of y over x, or the inverse tangent of y over x plus pi, or plus 30 or plus 180 degrees. So you have to be, it's a little bit trickier to go from rectangular to polar coordinates, but just because of the way we find theta with the inverse tangent. Now let's look at equation conversion. Let's go from polar to rectangular. Here is a polar equation. Now this would be a circle. This is just saying r is equal to 4. It's a circle with a radius of 4. And you can see this is a very simple way to write an equation for a circle. Remember, with using rectangular coordinates, we would say x squared plus y squared equals 2 squared. So using rectangular coordinates to describe a circle is a little bit more complicated than here. Here, we just r equals 4. It's very simple. But now we want to look and see, well, how do we convert that to the rectangular coordinate system? We want to remember our relationships. And we remember this, that r squared is equal to x squared plus y squared. So I'll just square both sides, and look at this. I do get an r squared. Now whenever I have an r squared, I can replace that with x squared plus y squared. So here we have our equation. Now I think I misspoke a minute ago. I said that a radius 4 would be x squared plus y squared equals 2 squared. It would be x squared plus y squared equals 4 squared. So I misspoke. But anyway, here is the equation that we're searching for. Okay, so we convert it from polar to rectangular. Notice polar does look simpler than this. So that's why I said earlier, sometimes we're going to find it's more convenient to work with the polar. Not always. Okay. Now, let's look at polar to rectangular. Another example of polar to rectangular. So here we go. We've got r equals sine theta. Now we have some a formula for conversion that looks almost like this. We have r sine theta. We know that when we see r sine theta, we can replace that with a y. Well, we don't have r sine theta, and we don't have r squared either. But I can fix that by multiplying both sides by r. Now look what I have. I have r squared equals y, because r sine theta is y. Now I'll replace the r squared with x squared plus y squared, and we have our conversion here. R equals sine theta, and now we have x squared plus y squared equals y. So we've gone from a polar equation to a rectangular equation. Okay, let's look at another one. Let's suppose we have this polar equation. Theta equals pi over 6. Okay, well, we recall this, that tangent theta is equal to, well, in this case, since theta is pi over 6, tangent theta is equal to tangent of pi over 6. And we know that tangent of pi over 6 is 1 over the square root of 3. From the unit circle, by putting the sine of pi over 6 over the cosine of pi over 6, we get 1 over the square root of 3. Now, we have that tangent theta equals 1 over the square root of 3. That's what we have so far. And remember, tangent is just y over x. So if I multiply both sides by x, I'll have my conversion. So that's kind of a tricky one at first. When you first look at it, it's a little bit tricky. But what you do is you say, well, tangent equals this, and it also equals y over x. So I replace tangent with y over x, and I get 1 over the square root of 3 and then solve. So a little bit tricky. Now let's go from rectangular to polar. Here's a nice familiar rectangular equation. The equation for a line. Now we want to convert this to polar form. So here we go. First of all, you recognize that this x can be replaced by r cosine theta. And the y can be replaced with r sine theta. Now the only thing left to do is to solve for the r. And you want to do this whenever you can. I'm going to solve this equation for r. And I do so by just factoring out the r. You notice I have an r here and here. So I'll just factor that out. And then divide by this big, long coefficient of the r. And I get r is equal to 5 over 2 cosine theta plus 3 sine theta. And there we have our conversion. So we've successfully converted from this rectangular form to this polar form.